Good afternoon, everybody. Welcome along to a lunchtime lecture today, which is going to be given by Pieter Vermeesch, who's in the Department of Earth Sciences here at UCL. Pieter did his BSc in geology at the University of Ghent in Belgium. And he then did a master's at MIT and his PhD at Stanford. So he's been through some fairly prestigious academic institutions. He got an RC UK fellowship at Birkbeck in 2007, and then moved over the road here to UCL in 2012. Pieter has a very good academic career, but also he has other talents, one of which is running. And when we're sampling sand dunes, we collect samples from the crests of the dunes, and these sand dunes can be sort of 60 or 70 meters high. And so we send Pieter out running to get the samples. And Pieter's time for the London Olympics, I think, is 2 hours, 19 minutes. It's pretty good. Sorry, the London Marathon, not the Olympics, sorry, London Marathon was 2 hours and 19 minutes. And the other day, you did 50 kilometers in under 3 hours? Yeah, he's pretty quick. Right, so Pieter will be talking about sand, tracing sand through the deserts, using remote sensing and cosmogenic dating. So over to you, Pieter.
Thank you very much, Charlie, and thank you, audience, people on the internet, for attending this lunch hour lecture. So in the next half hour, I will talk to you about some of the research that I've been doing since coming to England, since coming to Birkbeck and then University College London, research that has focused on desert sand. And I will walk you through a number of case studies that span quite a wide range of timescales and that use a range of different techniques. So I will show you some examples of research that studies the mobility of desert sand over months to years to decades using satellite imagery, and I'll move to millennia and millions of years using principles of sedimentology, geochronology, and some statistics. The field area of the first few case studies, I wonder if the light could be dimmed. Is that possible? I don't know if you can see it. The first few case studies will be focusing on the Bodele Depression in northern Chad in the central Sahara Desert. And the reason why I have chosen this godforsaken place is that it contains some of the world's largest and fastest moving, barchan dunes, sand dunes that are there because of a unique combination of two factors. First of all, the Bodele Depression is located just downwind from a narrow gap between the Tibesti and the Enedi Mountains between Libya and Chad. And this gap acts as a funnel that accelerates the northeasterly trade winds into a low-level jet, strong winds that have the power to move sand very quickly. A second factor is the fact that the Bodele Depression was located in the deepest part of Paleo Lake Mega-Chad, a lake that was rivaling the Caspian Sea in size as recently as 8,000 years ago. 8,000 years ago, people were fishing in the Sahara. We had hippos, we had lots of lake creatures living there. Now, all that water is gone, except for a little bit that is left in Lake Chad in the south of the country, but the sediments remain. And in the Bodele Depression, those sediments are not made of sand, they're made of crusts of diatoms, diatomite, fossils of plankton that used to live in this big lake, and that is now forming these white crusts on this ancient lake bed. So in this sequence of satellite images, Landsat images from 1972 to 2008, you can see that this white crust of diatoms, diatomite, remains stationary, whereas the dunes move on top from the northeast to the southwest in the direction of the horns of these crescentic dunes. That's the way that these barchan dunes should move. Another thing that we can see on this movie is that small dunes, such as this one here, move much faster than large dunes. And this tells us that the dune velocity or celerity in itself is not a very meaningful quantity. The sand flux, which is the product obtained by multiplying the height of the dune with its celerity, that's more or less constant across this area. That's a much more useful value to sand dune experts, to aeolian geomorphologists. Now, traditionally, these people, these scientists, measured sand flux by monitoring stakes that were planted in the interdunes, the areas between the dunes. Now, this is time-consuming, expensive, and in places like northern Chad, which are very unsafe at the moment, this is impossible. And this is why I've invented a method to measure sand flux automatically from space using overlapping satellite imagery. So in the first case study, I will use not Landsat images, but aster images, overlapping scenes, first in the eastern part of Benelli Depression, satellite images that were acquired in the year 2000, 2005, 2006, and 2007. Now, in principle, you could create an animation like I did on the previous slide, and you can measure the movement of the dunes by hand. But actually use a different technique, a more sophisticated technique to do this automatically using an algorithm that is called QuasiCore. QuasiCore is a change detection algorithm that was invented by geophysicists at the California Institute of Technology for the purpose of not measuring sand dune migration, but for detecting the movement of land caused by earthquakes. To this end, these geophysicists acquire satellite imagery before and after the earthquake. Then they divide the before image into a number of rectangular windows. And they move these around until you find the best match with the other image. And that produces a displacement map, an example of which is shown on this slide for the 1999 Hector mine earthquake, a magnitude 7 earthquake in eastern California near the border with Nevada in the United States. So this earthquake was associated with a movement along this plane, which is along this line, a movement of a displacement of 4.5 meters. And this was obtained from satellite images, from the SPOT satellite, the French satellite, the satellite image that has a resolution, a pixel size of 5 meters. So QuasiCore, this technique, has a sub-pixel resolution. So originally, this technique was developed to measure the displacement associated with earthquakes, but it was quickly realized that the tool has lots of applications in other fields of the earth sciences as well, such as, for example, the movement of ice in glaciers, such as this Mer de Glace in France, where QuasiCore has been applied to 2 SPOT satellite images that were taken just 26 days apart. Here, the change detection algorithm has tracked cracks and crevasses on the surface of the ice, and it has painted an incredibly detailed picture of the flow of the ice as it is moving down this 4,000 meter high mountain, where it is accelerating where the ice is steep and then slowing down where the ice is less steep. On the right hand side is an application of QuasiCore to a landslide, a slow-moving mass of rocks that is sliding down another slope in the French Alps, a landslide that had long been monitored by expensive GPS stations shown as circles. Here you can see that actually these conventional surveying equipment has basically missed most of the movement. But where there is some overlap between the two techniques, they agree very well. So QuasiCore is not only much cheaper, much easier to deploy than these conventional techniques, it gives you much better spatial resolution. And then last but not least, nearly exactly 10 years ago, I published the first application of the QuasiCore algorithm to sand dunes. Now, QuasiCore produces 2 maps, one with the east-west and one with the north-south displacements. And one way to combine these 2 maps is to show them as a vector field, as these arrows. Arrows that, again, confirm that the dunes move from the northeast to the southwest in the direction of the wind, the direction of the horns of the dunes, and that the small dunes move faster than the large dunes. So that's one way to visualize the data. Another way is to combine the east-west and the north-south displacements and plot the entire displacement. So you sum them basically in squares and take the square root of that, and then you get a map of the total distance traveled by these features in a 15-month time period, the time between the 2 satellite images that were used for the analysis. So this is the displacement map of some dunes that are shown in optical light on the left-hand side here. These are some of the world's largest active crescentic dunes. They have a horn length of more than a mile. They are more than 50 meters high, and they are made of fossils. Quite remarkable. Low density fossils which make them move very fast, more than 100 meters in places in just 15 months. So I said that I used the ASTER satellite for this analysis, and there are two reasons for this. First, ASTER is cheap. You can actually get it for free now from the NASA or the Japanese Space Agency websites. Second, ASTER has two cameras on board. One forward-looking camera and one rear-looking camera. So for every satellite image, you've got two different views on the scene. And that, just like we've got two views on the world with our eyes, allows us to see 3 dimensions. For every ASTER satellite image, you get a 3-dimensional digital elevation model included with it. And that allows us to measure sand flux. This is how you do it. So you take your displacement map, which shows the dunes, areas that have moved, and the interdunes, areas that have not moved, and then you select the corresponding parts of this topographic model. You draw a surface between the interdunes, the areas that have not moved, and you subtract the topography from this interdune surface. And then you get the dune heights. Dune heights, which again are more than 50 meters in this part of the Bodele Depression. If you then multiply the velocities of the dunes with the height of the dunes, you get another map. This is a map that has units of cubic meters of sand or of diatomite per meter of width perpendicular to the wind per day. This is a unit of sand flux. This is an economically valuable piece of information because it allows engineers to predict how much sand needs to be removed from roads and pipelines that are being constructed in desert areas. And it's much cheaper than the conventional way of monitoring stakes in interdunes for long periods of time. So that concludes the first part of my presentation, the very shortest, the mobility of sand over the very shortest timescales. Let's now take one step back and have another look at these animations, these time series of dune migration. So earlier I said that the velocity or the celerity of sand dunes in itself is not a very meaningful or useful piece of information because it's such a sensitive function of the height of the dunes. However, changes in the celerity of dunes are useful because they can tell us something about dust. The Sahara produces massive amounts of dust. This dust is fertilizing the Atlantic Ocean. It increases the reflectivity of our planet. This very white-colored dust reflects sunlight back into space. So a better understanding of dust production is important for climate models. The Bodele Depression in northern Chad is the single most important point source of dust on the planet. We can expect most of that dust to be ejected into the atmosphere during storms. And this is also when the dunes move the most. So we might expect there to be some correlation between the windiness of the Sahara and the dust production and the dune velocities. A correlation between dune velocity and dust. So I will try to extend the QuasiCore algorithm to accept not just 2 images, but multiple images and see if there's been any change in the speed of these dunes in order to quantify the total amount of work that the wind puts into the landscape. So to this end, I've acquired quite a large set of imagery. I've got declassified American spy satellite imagery from 1965 and 1970. I have a 1984 Landsat image. I've got spot satellite images from 1990 and 96, and I've got ASTER images from 2003, 2007, and 2010. I also acquired a small tile of 50 centimeter resolution GeoEye satellite imagery for an area that was visited by Professor Charlie Bristow in 2005. So at that time, Chad was relatively safe, and Charlie visited the Benelli Depression and he recorded the GPS coordinates of a Russian rocket launcher that was left behind from the war between Libya and Chad in the early 1980s. At the time, this weapon was hiding behind the steepest slope, which is this side, the lee side of this barchan dune, and shooting at the enemy. The vehicle was then abandoned, and it was quickly buried by the sand dune. 26 years later, the dune has now moved 600 meters towards the southwest, and the rocket launcher has emerged from the other side of the dune. So the purpose of the next part of my presentation is to show you how the QuasiCore algorithm can be extended to automatically extract these paths from sequences of satellite images. But before I do that, I would like to tell you about another serendipitous discovery that I have made by looking at these animations of moving sand dunes for an awful long time. In 2003, Veit Schwemmler and Hans Hermann of the University of Stuttgart, and now in Zurich, published a controversial numerical, so a computer model prediction. A prediction that said that when two barchan dunes, two crescentic dunes collide, which they can do because small dunes move faster than large dunes and inevitably catch up with large dunes. When they collide, the small dune can appear to travel through the large dune as if it were a solitary wave, like a water wave. Now this sounds crazy, but actually the mechanism is quite plausible. The idea is that when the small dune travels faster than the large dune, eventually it catches up with the large dune and it then shields the large dune from the wind and from the supply of sand. So the large dune is starved of sand, it shrinks and it speeds up. The small dune grows because it scavenges sand from the large dune. It grows, it slows down. When you squint your eyes, you look at it from a distance, it appears as if the small dune travels through the large dune. Plausible though this might be, it was nevertheless a very controversial prediction because this phenomenon had never been observed in nature before. Now, if there's one place on our planet where we might be able to see this phenomenon playing out, it would be the Bodele Depression, because in the Bodele Depression, the aeolian processes, dune movements, is magnified and accelerated due to the strong winds and the low-density diatomite sediment. So, lo and behold, when I looked at these animations, I found multiple instances of solitary wave behavior, a number of examples of which are contained or shown on this website. See the URL in the upper right corner here. So here's an example. I've got a declassified American spy satellite image. By the way, if you're looking for spy satellite imagery of countries like Chad that were in the Soviet sphere of influence, you should go to the Americans. If you want to find satellite images of America, you have to go to the Russians. They're very complementary. The Chinese cover both. Not easy to get hold of their images, though. But the American imagery is very easy to get hold of. So we can get an image from the 1970s showing a small dune sitting just upwind from the large dune. It catches up with the large dune, it grows, it slows down, the downwind dune shrinks, speeds up. It does indeed appear as if the small dune travels through the large dune. A second model prediction, actually an analog model prediction, so an experiment that was done in a water tank, predicted that when two dunes undergo an off-center collision, so not head-on, but at a slight offset, then the small dune can appear to, well, can really rip off, tear off the arm of the large downwind dune, and then form a new baby barchan that spawns and takes off by itself. Again, I found several instances of this phenomenon playing out in the Bodele Depression. You can see the small dune catching up with the large dune, tearing off the arm, and that forms a new dune. All right, back to our main storyline. How do we extract time series of dune movement from these sequences of satellite images? Well, I simply feed them into the QuasiCore algorithm two at a time. So I've got 1984 to 1990, 1990 to 1996, 1, 2, 3, 4, 5, 6, 7 satellite images, 6 pairs. I have 6 displacement maps. These 6 displacement maps will show patches of mobility, a single dune or multiple dunes, that are moving over time. I had to do a bit of additional programming to then move all these patches of mobility back to a common point in time where I can then compare them and stack them on top of each other. So that common point in time is 1984. and I can visualize the results as a sequence of colored dots which are tracking the sand dunes automatically from 1984 to 2010 in map view. 1965 image, a corona satellite image, is shown as a gray outline. I could not really apply my automated algorithm to this corona satellite image because it's a remarkable technical achievement. In the 1960s, the Americans were sending a satellite every month into space, satellite of the size of a bus, into space, taking pictures on analog film. That was then thrown back into the atmosphere, intercepted by a military plane, processed, and it's just plain photographs, which of course warp a little bit. They're not as well behaved as digital images. So I had to do a manual correlation there. So this is one way to view the displacements of my sand dunes. I can also then simply take the step sizes and divide it by the amount of time elapsed between the different satellite images, the exposures that were used for the analysis. And that gives me a time series of dune celerity, velocity, for sand dunes of a particular size over time for about 2,200 displacements. This is the result of the automated analysis. I've done a manual analysis of 10 dunes going back to 1965. Now this is a bit of a negative result. I don't see any change. So there doesn't seem to be any change in the windiness of the Sahara. So any changes in the dust production of the Sahara must be due to other factors, such as land degradation, overgrazing, things like that. Okay, so that concludes the remote sensing part of my presentation. Let's now move on to much longer timescales and a different field area. So we will leave the Sahara Desert and go to the southwest of Africa, to the Namib Sand Sea, which covers an area of 30,000 square kilometers, the size of Belgium, on the Atlantic coast of southern Africa. Atmospheric circulation in this part of the world is dominated by the South Atlantic anticyclone. So the dominant wind is a southerly to southwesterly trade wind with infrequent easterly storms occurring in winter. So there are two wind directions, which is different from the Sahara where we've got one wind direction. Two wind directions and the availability of lots and lots of sand produce a different type of dune. So we don't have these moon-shaped crescentic barchan dunes. We've got linear dunes, large ridges up to 100 meters in height that are aligned in the resultant wind directions from the south to the north. So I would like to date the sand, quantify how long the sand resides within the deserts. But before I can do that, I need to first figure out where the sand came from. That's not very clear at this point. There are three possible sources of sand into the Namib Sand Sea. On the border between Namibia and South Africa, there's the Orange River. It's a large river, 2,000 kilometers long, that drains most of southern Africa, dumps its sediments at Oranjemund, or Alexander Bay on the South African side. That sediment is then carried up the coast of Namibia by strong currents and enters the desert at a town called Ludritz. So that's one source of sand. The second source of sand are these ephemerals, so dry rivers that occasionally flood and that are draining the escarpment that rises steeply towards the east of the Namib Sand Sea. With the exception of the Kuisep River, which marks the northern boundary of the Namib Sand Sea, none of these ephemeral drainages reach the ocean. Instead, they dump their sediments into shallow depressions or vlays, the most famous of which is the scenic Sossus Vlei, one of Namibia's main tourist attractions. And then finally, these hatched pattern here outlines some outcrops of the Tsondab sandstone formation. It's an ancient sand desert that is preserved underneath the modern sand deserts. So we'd like to figure out where that sand comes from. There are many ways of doing that. This is a branch of sedimentary geology called provenance analysis. The provenance of sediments can be inferred by characterizing certain properties in the sediments. We can measure the chemical composition of the sediment. We can separate minerals from the sand and count the occurrences of different minerals such as rutile, zircon, kyanite. You can recognize those if you're a trained geologist, and you can count their occurrences. They are a characteristic fingerprint that can allow you to distinguish between different sources and trace the flow of sand through a sediment fairway, as is shown on the right-hand side here. And then, or the left-hand side for you. And then a third way of doing it, so we've got the chemical composition, we've got the minerals, and we can also extract a single mineral, such as zircon, for example. It's a mineral that contains up to 0.1% of radioactive uranium, naturally occurring radioactivity that gives rise to lead. Uranium decays to lead. We can use that to measure the age of individual sand grains. And that age tells us whenever the sand grain formed in a magma chamber far away, long time ago, ages that go back billions of years. We can very quickly, with a laser, date, let's say, 100 grains of sand, and we can plot these ages as a bar chart and identify peaks of ages. We can compare those ages to the geologic map and figure out where the same sand came from. So I've used all these techniques and applied them all to the Namib sand sea. So I've got 16 samples from the Orange River and from the Namib sand sea. It was a lot of fun collecting those samples. And in those samples, I've analyzed the samples with 5 different techniques. I've dated sand grains between 0 and 3 billion years. So I've got a lot of grains at 1 billion years. I've got a lot of grains at about 600 million years. I've got fewer grains that are older than that. But the relative frequencies of these different age components vary between samples. It's useful. I can measure the mineralogical composition. So I've got garnet, epidote, clinopyroxene. These are all different minerals. I was hoping to find diamonds, but I didn't. That would have been very useful. I've got other minerals, main components, different rock fragments that are found in the sand. I've got the chemical composition, a lot of data, about 20,000 numbers in this data set. It's really impossible for the human brain to process this and to see any patterns in here. We need some statistical help. And I have found a technique called multidimensional scaling. Sounds very complicated, but it's very simple. I found it very useful for making geological sense of these big data sets. So multidimensional scaling is, I think, best illustrated or explained with a simple geographical example. So this here is a table of distances between American airports. The distance between Atlanta and Denver is 1,212 miles. The distance between San Francisco and Houston is 1,645 miles. This is a table with positive numbers, all greater than 0, except for the diagonal. And it's symmetric. So this number is the same as that number. Where's my mouse? There we go. So these are all the requirements, really, that we need to perform multidimensional scaling analysis. We put this table into a computer program called MDS, and it spits out a map of the United States. So we've got New York City in the northeast, Miami in the southeast, Seattle in the northwest, Los Angeles in the southwest. Right? Fairly simple. We can do the same with my sand samples. Of course, I will not express distances in miles. I will have some statistical distance. There are many ways of doing that. The details do not matter. But it will spit out a map. I've actually applied this not only to sand from the Namib Sand Sea, but sand from all along the southwest African coast. From South Africa to Namibia, to Angola, up the Congo River. I've got lots of sand, many field seasons. I've characterized them in all these different ways. I've put them into this MDS algorithm, and the results are quite striking. You can see that there's a very close association between the geography, the locations where these samples were collected, and the MDS map. It tells me that sand from the Orange River travels up the coast of Namibia all the way to southern Angola. All the sand is basically indistinguishable in its composition and in its ages of the individual sand grains. And then all of a sudden, it changes completely. And we get Angolan sands, which continue for 1,000 kilometers towards the north. There's a very discrete point. It's a town called Namib in Angola, where all of a sudden the sand from the Orange River terminates. Actually, it disappears into the Atlantic Ocean. And that continues all the way until the border with the Congo, where all of a sudden you get then another signature. So it appears that the sand in the Namib Sand Sea is derived from the Orange River. Actually, if we zoom into this field area, so here are 2 samples of Orange River sand, and this is the Namib Sand Sea. We can see that the sand along the coast of the Orange River all these samples plot close together. So these are very similar compositions. The sand along the coast is all derived from the Orange River. Sand inland, N4, N5, N9, N8, have a small contribution from these ephemeral rivers draining from the escarpment. So from this analysis, we can tell that the sand comes from the Orange River, then moves up north, enters the Namib Sand Sea, and then continues to travel towards the north, being buried by sand dunes, re-exposed, and gradually making their way towards the north. That brings me to the final part of my presentation. I would, now that we know that the sand, at least along the coast of the Namib Sand Sea, comes from the Orange River, I would like to measure how long it takes for the sand to get from Lüderitz to Walvis Bay. And I will do that using another dating technique called Cosmogenic Nuclide Geochronology. It's based on the fact that the Earth is bombarded by cosmic rays, high-energy protons and neutrons that are produced by supernovae across the galaxy. They bombard our planet. Many of them get deflected by the Earth's magnetic field, but some collide with the Earth's atmosphere, and they react with the oxygen and the argon in the atmosphere, and they weaken in intensity as you go deeper and deeper into the atmosphere. So we are protected from this radiation by the atmosphere and the Earth's magnetic field. Nevertheless, some of the highest energy particles do reach the surface of the Earth. And these high energy neutrons continue then to interact with the rocks and the soils and the atoms contained in the rocks and the soils on the surface of the Earth. When a high energy neutron collides with an oxygen, a silicon, an iron, magnesium, whatever, any element in the Earth's crust, it produces nuclear reactions. These atoms, these target atoms, explode, form smaller secondary atoms, cosmogenic nuclides, some of which we can use to date how long a rock has been exposed to these cosmic rays. So if you measure the concentration of beryllium-10, for example, beryllium-10 is a radioactive element. Its intensity, if you leave it untouched, decreases, is halved every 1.3 million years. There should not be any beryllium-10 on planet Earth. The only way that we can explain the existence of beryllium-10 in the uppermost 1 meter below the surface is because it's produced by cosmic rays. If we measure the concentration of beryllium-10 in atoms of beryllium-10 per gram of rock, and we know the production rate in atoms per gram per year, then we can measure how long the rock has been exposed to cosmic radiation. It's similar to estimating how long a person has been exposed to sunlight by measuring their skin tan, or in my case, the redness of my skin when I'm exposed to sunlight. That's why I had that picture there. Right, so what happens to our sand in Namibia? Well, that sand comes from South Africa. As it travels down, as it is eroding and sitting at the surface of entire southern Africa, it's irradiated with cosmic rays. It then travels down the Orange River. It acquires more cosmogenic nuclides, not only beryllium-10, but also neon-21. That's another cosmogenic nuclide. Its concentration increases until it reaches the Atlantic Ocean. It's washed up the shore of the Atlantic Ocean. It enters the Namib Sand Sea in Lüderitz, and it's buried by 100 meters of sand in these large sand dunes. The sand is then shielded from cosmic radiation. No new beryllium-10 is being produced. The radioactive decay of beryllium, however, continues. And so as the sand is quickly re-exposed, enters another desert, is buried again, it loses beryllium-10. Neon is another cosmogenic nuclide that is not radioactive. It will not decay. But so what we could expect to find, and this is actually a figure that I put in a research proposal to get some money for this research, I predicted that sand in the Orange River should have a certain concentration of these cosmogenic nuclides. It should have almost the same concentration in the south of the Namib Sand Sea because it travels down this coast or up this coast very quickly. And then the cosmogenic radionuclides, beryllium and aluminium concentration, should decrease as the sand moves slowly from the south to the north, being buried in the sand in the dunes most of the time. And the degree of resetting of this cosmogenic signal should allow us to date, measure how long it takes for the sand to get re-exposed. Now, neon-21 is not radioactive, so we would not expect it to reduce as we travel to the north. if anything, it should either be constant or slightly increase every time the sand escapes from a dune. Before it enters another dune, maybe a bit more neon-21 would be added. So it's a very useful background check that we could use there. So these were the predicted results, and these are the measurements. It's not perfect, but actually it's a rare pleasure in science to have measurements match the predictions so well. We do indeed see beryllium decreasing from the south to the north. Aluminium is decreasing faster because it is more radioactive and has a half-life of not 1.3 million years, but 700,000 years. Neon is difficult to measure, but is essentially constant. So this degree of resetting allows us to date the residence time of sand in the Namib Sand Sea to 1 million years. And that concludes my presentation. Thank you very much for your attention.
Thank you, Pieter. A tour de force there of all the dunes around North Africa and Namibia. Do we have any questions? Yes. Someone's coming with a microphone.
Hi, thank you for the presentation. And my question was about the smaller dunes traveling through the bigger ones. Since they absorb all the sand and starve the bigger dune of the sand before they go in there, how do they continue afterwards? Because shouldn't the effect be reversed and they would be starved of all the sand and like the movement?
So you mean when the small dune catches up with the large dune?
Yes.
Microphone. The small dune catches up with the large dune, the large dune shrinks, and the small dune grows, it takes off, and you would expect to then
why does
catch
it
up again?
move on as two separate waves and not two separate dunes and not stay in one big dune since they have the same exposure?
This has been studied, so there's actually, this only works if the ratio of the sizes of the dunes falls within a certain window. If the small dune is too small, it will be absorbed by the large dune. It's only in a narrow range that this solitary wave behavior happens, yes.
Okay, next question.
Not a very scientific question, but how long did it take you to take all these samples? How many travels did you have to do? Or was it in one day?
No. So I went to Namibia the first time in 2009 and the second time in 2012 with Charlie, who was an excellent dune driver, because initially I collected sands along the edges. But I was very keen to also collect some sands here. It's not very easy to get there. Actually, on the first field expedition, I was traveling around here, and over here we saw some tourists going into the desert. I said, hey, can you go into that desert? I said, yes. So then a few years later, we joined a tourist group and drove across this desert. It's an amazing adventure. So that was the second trip. Then I had one trip all the way up the Angolan coast. I did that in 10 days. It was a lot of driving. And then the Congo was last year, so there are 4 trips. Yeah. So, yeah, lots of driving though. It's not always glamorous, but still, interesting places.
So, Willie, you had a question?
Very good question. So the production rate of cosmogenic nuclides, the number of atoms of beryllium, aluminium, neon per year, per gram of rock or mineral, depends on the latitude and the longitude. It also changes in time as the magnetic field strength of the Earth changes. So we know the production rate. So in order to calibrate the production rate, you need to have an independent age constraint. So, for example, a retreat of a glacier that has also been dated. So when a glacier moves on rocks, it removes rock, it scratches the surface, and then if you could then date this surface, you measure the cosmogenic nuclide concentration in that surface. If you have a radiocarbon date for that same surface, then you can use that to estimate the production rate. Now, there are only a few dozen of these places around the world where we have independent age constraints that allow us to calibrate the production rate. And in all other places in the world, you have to extrapolate. And especially at low latitudes, this is difficult. We don't have a lot of calibration sites at low latitudes, and there is definitely some uncertainty in that. Now here, I don't really care about this because I'm just looking at, they all have the same source. They all start off with the same cosmogenic nuclide concentration. I don't really care about the age of the of exposure in South Africa. All I care about the residence in the Namib Sand Sea, and that's not so sensitive to the production rate. But if you want to really date archaeological remains, for example, that has also been attempted with cosmogenic nuclides, and you're very vulnerable to those challenges of extrapolating production rates from a few places to other parts of the world.
Thank you, that was very interesting. But apart from being interesting, why is this information useful?
Well, I told you that the sand flux measurements are useful. In fact, I was affiliated with a Caltech spin-off company called Imagine Labs that was selling these services, measuring sand flux, for example, to construction companies in desert areas. That's definitely very useful. Why this is useful? Well, there's not an immediate economic benefit, but I think it's widely recognized that climate change is a big topic. And really, we are confirming here that the sand desert is extremely old, even without any anthropogenic change. That climate there is very stable. And so cosmogenic nuclide geochronology has really revolutionized our understanding of the glacial history of Europe, and now also the history of arid lands. And remobilization of sand deserts, we can date when the Kalahari, for example, was last active. And now it's slightly overgrown, but it might become active again. And so these cosmogenic nuclide dating definitely has policy implications. So yeah, that's my answer to that question.
Okay. Any other questions?
What do you mean by the desert becoming active again?
Yes. Well, so in some parts of the world, for example, in Saudi, we were in Saudi, in 50 years ago, the dunes were all mobile, and now they're overgrown, right? In the Kalahari, there are concerns that the opposite will happen. At the moment, the Kalahari is like a semi-desert. There is some grass. If that grass disappears, you create the biggest sand sea in the world, and then anybody who lives in Botswana would really be vulnerable to, just desertification. There would be no grass for the animals to eat. So when the desert is really at the tipping point of becoming, when the sand has at the tipping point of remobilizing, you've got the Nebraska sandhills. It's a nice grassland, but how long ago, Charlie, you're an expert on the grasslands, it used to be a sand desert like the Sahara, and you don't need a big change in annual rainfall to change that grassland into a sand desert. And that would be disastrous for the people of Nebraska, right? So cosmogenic nuclide geochronology can help us date when was the Nebraska sandhills last mobile. Very useful information that we did not have before.
Okay. Any other questions? All right. Well, I think it's time to thank Pieter again.